Hello, everybody. This is Miss Peachy from your WCA Physics A class, and we are in Unit 6, Lesson 2 on momentum. The words that we have today are closed system, conserves momentum, impulse, mass, momentum, Newton's second law of motion and velocity, and we're going to kind of go into some more details with those as we go as well. I'm going to go ahead and just extend this a little bit. I don't really need quite as much space on the whiteboard, but I do need a little bit more space here. So today we're going to specifically introduce what momentum is, and then we're going to look at the impulse momentum theory as well and how momentum relates to, how it relates to Newton's second law, which is important as well. So let's kind of go through what momentum is. I'm going to do a little bit of reading here from the lesson too. So this part here in the first slide is talking a little bit about different balls and which one has a greater momentum. So it's comparing a basketball to a baseball. So our basketball is 0.6 kilograms traveling at 5 meters per second, and our baseball is only 0.15 kilograms, but it's moving faster at 50 meters per second. So it asks you to calculate which one has more momentum. Momentum is a fairly simple equation. So look at the equation for momentum. The equation is, and I'm going to go ahead and choose this. It is P equals mv, right? Just like that. So pretty simple. Mathematically, you're just multiplying the mass times the velocity. The mass does have to be in kilograms, and the velocity does have to be in meters per second. So then our label, our units for momentum are kilogram meters per second. You multiply those. I know it's kind of weird to think of a unit as something where you actually have a math function in it, but a square is a math function as well. So multiplication is too. So it's really very normal in physics to see multiplication in the units, division in the units. So, you'll see kilograms times meters squared here. Actually, kilogram meter per second squared, my bad. There we go. Times meter per second squared, and that is very normal, very normal function. Just basically as a reflection of, the units and what we're doing with the problem. In the problem, we're taking mass and we're multiplying it by velocity. So in the units, we take mass units and multiply them by velocity units as well. So when we do this, let me go ahead and just clear that off of there. You can calculate the momentum. It talks about some problems. A truck driving along the highway has a large quantity of momentum because it has a high mass. If it moves at the same speed but has twice as much mass, what happens to the momentum? So we can just say, let's say, the momentum, momentum is equal to mass times velocity. If we double the momentum or double the mass, we're just going to take that m and multiply it by 2. We also have to double the momentum because according to the rules of algebra, what we do to one side of the equation, we must do to the other side of the equation. So if I double the mass, my momentum is also going to double. So what happens is it doubles. It's 2 times because they are directly proportional to one another. If you increase one, the other one also increases by the same amount. All right, so, another problem here, a golf club head with a mass of 0.2 kilograms is swung and collides with a stationary golf ball of mass 0.05 kilograms. The golf club is traveling at 40 meters per second when it touches the ball. What is the total momentum of the system? So here we start talking a little bit about how, when we're looking at momentum, we have to kind of think of interactions that are involved here. So here it says describe the momentum of the club ball system by substituting the known values for the club's mass and speed into the equation. So in this particular example, we're calculating the momentum of the club essentially right when it touches the ball. So not after it, but right when it touches it. So all we need to do is take the mass of the club, which is 0.25 kilograms, and multiply it times the velocity of the club, and that gives us 10 kilogram meters per second. So that gives you the momentum of the club just before it touches the ball, because that is kind of what the question is asking for. But then let's say we have a system where we want to figure out the momentum when they touch, like before and after. How does that change? Because we have collisions that occur, which are where two different objects that have different momentums interact with each other. So it talks a little bit about how we have to think of a closed system. A closed system is where we have an exchange of energy, but never with matter for the environment. So we end up with what's known as conservation of momentum. And this is one of those ideal systems that are a model of what happens in the real world without being exactly what's happening in the real world. So we're taking out any kind of like complex interactions that are that make it simplifies it essentially. It makes it a little easier for us to understand, a little easier for us to be able to do calculations and things like that. So it's not necessarily what's happening in real life. No system we know of is truly a closed system, but we're just dealing with one closed system here. So here's an example of we have billiard balls, which are like pool, the game of pool, right? And we have ball one has a certain amount of momentum, and this is calculated as P equals mv. And then we also have ball two. Initially, ball two is um, at rest, and ball one is moving. And then when ball one hits ball one is at rest, and ball two is moving in this situation. That's what's going on. So I'm going to go ahead and draw a picture. We're going to do it over here. So if we have ball one, and it is in motion, right? And it collides with ball two, which is stationary. And then after the collision, ball one is stationary and ball two is in motion, right? So they're just kind of flip-flopping in this situation. So the momentum was transferred from ball one to ball two in this situation. We're not going to deal with any other interactions. No momentum in this ideal closed system is being transferred to the pool table. None of it is being transferred to the pool cue that you're using to actually, hit the balls. So we're going to ignore any potential transfer of momentum outside of this closed system. So what we can do is we can calculate the momentum of each of these balls independently. So here above, this is before the collision. And here is after the collision, right? And we can calculate the momentum of ball one, because ball one is, you have the momentum before the collision. And we'll call that P1 before. And then we'll have the momentum of ball one after the collision, that is P1 after, P1A. And then we have the momentum of ball two, which we'll call P2 before. And then we'll have the momentum of ball two after, which is P2 after. Okay, so what they're saying is that in a closed system, the momentum of both objects before collision is the same as the momentum of both objects after the collision. That while the momentum of each object individually changes, the momentum of the sum of the two does not. So that's what this is all about right here. Right here, right? So P1 before plus P1 after, you're adding those two together right here, plus together is equal to P1 after plus P2 after. They're equal to each other. So again, individually, the balls are going to change. As we said, the first billiard ball is moving and the second one was stationary. And then when they hit, the first one is stationary and the second one's moving. They're kind of flip-flopping in here. But they're going to be, if you add them up together beforehand and after, they're going to be the same. So let's see here. Let's give an example. A ball one is moving with a momentum of 5 kilogram meters per second. So that's what this one has. It strikes ball two, which is at rest. So this has a momentum of 5 kilogram meters per second. But this ball two has a momentum of 0 because it's not moving. So if it's not moving, there's no velocity. Doesn't matter what the mass is. Anything times 0 is 0, so no momentum. Afterwards, ball A has a momentum of 0 because it's not moving, and ball two has a momentum of 5 kilogram meters per second, right? Because it is now in motion with the same velocity as ball one had before. So that's kind of our solution, and that's how we see conservation of momentum there. It's not always going to be like equal in that situation. It kind of depends on the type of collision that we have. Let's look at example 2. Suppose that, as with the previous example, the balls bounce off each other. After the collision, ball 1 is moving to the left with a momentum of 2 kilogram meters per second. What is the momentum of ball 2? So let's look at that example here. So we're going to erase all this, and we're going to give that one another go. Okay, so we have ball 1, which is moving again to the right, and its momentum is, we said, 5 kilogram meters per second. Ball 2 in this scenario still starts off with a momentum of 0. Okay, so we know that the sum of them is equal to the total momentum, so 5 kilogram meter per second, right? Because that's what we do. We're summing the two together. That's our before the collision. So this is before. Afterwards, whoa, hang on a second, I accidentally dragged instead of drew. So afterwards, now ball 1 is moving in the opposite direction. It has a momentum of 2 kilogram meters per second. But because it's going in the opposite direction, we don't say it's 2, we say it's -2. Because this is a vector. So our positive and our negative signs are going to indicate direction here. So it's -2 because it's moving in the opposite direction. So -2 plus something, I don't know what it is, I'm going to call it P2. P2A, we'll call it P2A because that's our momentum after. That's what we've been using. Should still be equal to 5 because conservation of momentum, right? So we have to solve this. I want to get rid of the -2 on the left so I can isolate P2A. If I have a -2, I'm going to have to add a +2 to it, plus 2. Add +2 to the right side, and our final answer is P2A has a final momentum of 7 kilogram meters per second. So ball 1 moved to the left, ball 2 flew off to the right with a momentum of 7 kilogram meters per second. We can figure out the momentum of ball 2 because of the law of conservation of momentum, because the before momentum total sum should be equal to the after, the sum of. So that's how we do that problem. Oh, I used to be able to just erase the entire canvas, but it's just not being as cooperative. So we're just going to Use my little eraser. All right. So moving on to our next page, we're talking about how momentum is related to Newton's second law. Remember Newton's second law, force is equal to mass times acceleration. This one says that momentum is equal to mass times velocity. You kind of see that they're very similar to one another, right? So let's look at that. Force is equal to mass times acceleration. Well, we know that acceleration is just change in velocity over change in time. So I'm going to substitute change in velocity, or delta V, over delta T here. Okay, that's what force is equal to. Well, if I wanted to, I could move the T, get it out of the denominator. So I'm going to multiply both sides times delta T. And that cancels out here. And then multiply the other side times delta T. Force times delta T is equal to M delta V. Oh, hey, that looks a lot like momentum. It is. Change in momentum. So the change in momentum is equal to force times time. That's what this is saying. So this basically tells us that this is what the impulse momentum theorem is. This is impulse. So change in momentum is what's known as impulse. We can write this as impulse. Or relabel it as that. In fact, you still want to have the momentum, change in velocity, or whatever. But the idea here is that if you allow that change in velocity to take place over a long period versus a short period of time, that affects the force applied to the object. And a great example to illustrate the impulse momentum theorem is thinking about a falling egg. This is one of my favorite examples. So say I have a hard floor here. It's like it's a cement floor. And I'm going to drop an egg from a certain height onto the floor. And it's going to make a mess. You know that because that's what happens. If the egg falls from a certain height, it will reach the floor and be at a certain velocity because the velocity is dependent upon the height. You know, the higher you hold that egg, the faster it's going to be hitting when it gets to the ground, right? It'll have more kinetic energy, therefore it'll be traveling faster, and so on and so forth. So it's going to have a certain amount of momentum depending on the velocity and its mass, right? So the momentum here is going to be equal to the mass times the velocity, right? If instead of dropping it onto a floor, I have created a nice soft pile of pillows and stuff here. My pillow. It's the same height though. So I'm not talking about that it's six inches higher or whatever. It's like embedded into the floor so it's nice and soft and cushy. And I'm going to drop the ball from the egg from the same height. And instead of hitting a hard floor, it's going to hit a pillow instead. It still has the same momentum, same mass, same velocity, but it doesn't break. So momentum's the same, but it doesn't break so something's different. And what's different is the impulse. The fact is that the change of momentum takes place over a longer period of time, which means you're reducing the force applied to the egg because the impulse is force times time. If time is going to be increased, then force goes down. Because the momentum, this is probably a better way of looking at it, the momentum is the same. So if my momentum is the same regardless, if I increase time, you have decreased force in order to get the same momentum. If I decrease time, force has to go up to get the same momentum. Does that make sense? So what's changing here is time, and then of course force is inversely proportional to that. So that's why the egg doesn't break when falling onto a pile of pillows from the same height, because you're reducing the amount of time of that collision. You're making that. That's also why seatbelts work. That's why your seatbelt works. You have the same momentum change, regardless if you're belted in or if you're not belted in. But what seatbelts do, aside from just keeping you in the vehicle, is they reduce the amount of time that force is applied to your body, because you get to move forward just a little bit. That's also why like airbags work really well. It's probably a better example. It's reducing the amount of time before you hit the steering wheel, so it doesn't hurt so much when you hit the steering wheel, right? All right, so that is your impulse momentum theorem. And I believe that is kind of the gist of everything in this lesson. There's some examples of that. There's also like a weird example with a mantis shrimp and how the exoskeleton of the mantis shrimp helps to kind of increase or decrease the impulse um, or force applied to the body of the shrimp or whatever. I don't know. Read through that one. But that's pretty much the gist of all the kind of the content in this lesson. If you have questions, let me know, or otherwise, you guys know we will see you in the next lesson.